So today we're going to go over Buffon's needle problem. And this is basically a method of estimating the value of pi. So it involves dropping two lines, which you can see here, and dropping a needle so that the center point falls between these two lines. And if you calculate the probability that the needle crosses one of these lines, then you can use that to estimate the value of pi. And in order to calculate this probability, we basically drop the needle a bunch of times. And then we count the number of time it crosses one of these lines and divide that number of time it crosses by the total number of times we dropped it. So here we have a small Python program to demonstrate this. So what this thing is doing is, first of all, we tell it how many times we want to drop it in order to estimate the probability. And then this is making some visuals for the two lines and the needle. This is using a library called random, which we use to randomly drop a needle somewhere. And this is basically telling whether or not we cross one of these lines. And this is actually calculating the probability, or estimating it in this case, since we can't do it an infinite number of times. We're doing the number of times we put to it in this statement. And then here we're using the probability to estimate the value of pi. And what this whole program basically does is it keeps dropping the needle, and then it updates the probability and the pi estimation each time. And here, using this, we can see what the pi estimation is. So if we run this, and then, I don't know, let's do it 20 times. Here, this is drawing the two lines. We're estimating the value of pi. And we see here we get a value of pi which is not very close, but it's still better than nothing. It's 0.5 round that away from the true value of pi. So if we again, and let's do 50, 40. And you see we're getting pretty close, a lot closer. This is very close to 3, and the value of pi is around 3.14. So if we, for fun, decide to do 100, needles, which we're using in order to create the needles, if you're curious, we're actually using a Python library called kernel. Creates pretty convenient graphics. And see, we're going to something even closer to 3.14. It seems to have diverged a little here, but here we get it pretty close. So if you're curious about why we're able to calculate this, here is a very good explanation for proof online using this link. And basically what it does is take some arbitrary angle because the needle can fall at any angle. That's the point of the problem. And it names this angle arbitrary angle theta. And what it does is it calculates the horizontal sort of piece of theta, of the needle, by using this formula, 1/2 which derives from the length of the needle, and then 1/2 of that times sine of theta. If you don't know what sine is basically a function that we use to calculate this portion, this straight line here, vertical portion. And here, what we're doing in this graph is we're basically plotting for each value of theta from 1 to pi. We're using a different units. You're probably using degrees to calculate angles. Here we're using a different type of unit called radians. This is why we get a pi here. And here what we're doing is calculating the maximum possible value for this vertical component here, such that it crosses one of these lines. So that's what this inequality here does. And in order to find the number of times it crosses the line, we're basically going to have to sum all of these values up, which is equivalent to finding the area under this curve here. If you want to learn more about this, you should learn about something called integration, which is a concept in calculus. And we use integration to find this area under the curve. If you want to learn more about that, you can explore that yourself. And then we divide that by this total area of this rectangle. That would basically be length times width, which is 1/2 pi, which is the area. And then here what we're doing. So we find the integral for the length of this needle with E being equal to 1 here. And then so it turns out that the area under that curve would be equal to 1. So this is why we have 1, which is the equivalent to the number of times the needle crosses the line, divided by the total number of counts. The reason why these are decimals is that we're using sort of different units for the number of times process and the number of times we drop it. And then here pi over 2. And then here we get 2 over pi, which is the probability. And then that means that we get this as a probability. So we can, using this and this, we can reverse engineer this so that basically we divide this pi, we divide 2 by the probability this, and then which is what we're doing here. Width because because we set this so we doing a different length for the needle. But that's how we get pi, and this is the proof. And that's all for today. Thank you for listening.